Thank you very much. First, I want to thank the organizer for giving me this great chance to speak here. So first, let me start with a definition. So let me start with the singularity. So it's a local picture. And then I put my variety in some Cn. So then I define the link of this point to be just the intersection of x with a ball, with a small ball which is centered on x. And we know that by Mironow's book, the local picture of the local topology of this one, topologically, is just a cone over this link. So in other words, this link basically carries all the local topology information of the singularity. Yeah, so by this I mean the boundary, the boundary ball, sorry, yeah. And so to understand this link, there are actually two simple layers to understand it. So first, by Mumford's work on normal singularity of surface, we know that if for isolated singularity of x, we can first take a log resolution. So by log resolution, I mean YE is a simple normal crossing, and this is what we call log resolution of x. So by Mumford's work, we know that to understand this local topology, it's very important to understand this E, this simple normal crossing divider. But of course, we easily see the definition of this simple normal crossing divider E depends on the log resolution, and even the topology of E depends on the log resolution. But we can look at the dual complex. So that's basically how we glue the different components of E together, the way we glue it. So by definition, we just write this. E is the sum of EI. And then for each EI, we correspond the vertex VI. And for the components of EI intersects EJ, we just correspond to the edges connects VI and VJ. And then you can imagine for components of three component intersection of three dividers, you just correspond to faces of VI, VJ, VIG, and then so on. So at the end, you just get a regular complex. You just get a regular cell complex. That's what we call DE, the dual complex. And this one actually, it's a theorem due to in different generality and by different approach due to different people. So to that people, actually, they prove that the dual complex, the homotopic type, is actually well defined. In other words, it doesn't depend on the resolution. So even the homotopic type of E may depend on the resolution, but the homotopic type of the dual complex doesn't depend on. So let me draw some picture to really give the proof. Which I mean, they probably use different approach, but the one I'm just going to give flows from the Pine's work, So basically, we just use weak factorization. So then we know that for two log resolution, we can basically connect them by blow up and blow down. So we just need to check for one blow up. And let me just draw a picture to let's say if I have three surface intersect in three folds, and then the corresponding dual complex picture will be, so these three divider correspond to these 2 points, and because they intersect with each other, so we just get a three-dimensional simplex. Sorry, two-dimensional simplex. And so there are two types of blow up. So I may blow up one strata of this picture. So for instance, I may blow up this point. If I blow up this point, I just got a I just got this one. And the dual complex will be, so this new point corresponds to this new exception divider. And because they also intersect in a way, so you basically just got a subdivision of the original complex. And also you may just randomly blow up some subvariety, but which is a simple number crossing with all this data. So for instance, I might just blow up a point here. Now if I blow up a point here, what I get is just a new divider here. And then if you draw the picture, fine. So because this divider only intersects with one of this divider here, so you just got a new point, and so you basically put a tail on this. So this corresponds to a subdivision. So this corresponds to so adding a cone. So basically, if I blow up this point, I got a new divider, and all the new cell complex I got just by adding a cone. But of course, in general, adding a cone is not a topologically trivial operation. But the point here is that the subvariety we blow up has to be on one single component, because it must be admissible blow up. So actually, we're adding a cone over a cone, in other words. So, but the cone itself is topologically trivial. So you're adding a cone over something topologically trivial, it's still topologically trivial. So that's how you prove that for these two different type of blow-ups, actually you don't change the homotopy type. And if you look at this, I mean, in general dimension, basically this gives the proof of the theorem. That's right. Well, I think there is one proof. The Terquilliers proof doesn't depend on the weak factorization. I don't know about this proof whether they need it. I mean, you use it? Okay. Okay. So I mean, there is one proof which doesn't need it. Yeah, but I mean for each step. But each step is. Yeah, I mean, so if you don't know weak factorization theorem, then for dominating, I mean, we cannot so analyze this, so we have to use the weak.
So the proof by Terquillier essentially says that the dual is homotopy equivalent to the backward.
That's right. Yeah.
And so it comes out of that.
That's right. Yeah, that's right. The Terquillier's approach is using the Berkeley space. So the main goal today is that, so here we had a homotopic invariant associated to a singularity. But indeed, we actually want to define the homomorphism invariant associated to a singularity. And why we cannot define it using simple number crossing? The point is, in surface case, the simple number, the local resolution is canonic. But there is a best one, which is called the minimal one. But in general, in higher dimension, the resolution usually it's quite complicated, and there is no minimal one. So there is no best one. So you have to look at all of them. On the other hand, minimal mode program provides some partial resolution, which carries more canonicity. But on the other hand, it's not a simple number crossing. So you have to first use the minimal mode program to construct some canonical object, and to show that this canonical object, which is defined not using simple number crossing pairs, is indeed the same as the one you define in the simple number crossing pairs. So that's the idea. So let me first state the theorems which I want to show. And there are a bunch of theorems using the same circle of ideas. So the first one, joint work with Tommaso, Delphinix, Janos, and myself, is that, so if I assume X is isolated, and I assume that the Q Grunstein, well, let's say, just this is Q Katia. That just means some multiple of let's say normal. So then Kx is always a Wave divisor. So Q Katia just means some multiple of this Wave divisor is indeed a Katia divisor. So you can always put it back. And then there is a this is just a regular complex. Which is well defined up to homomorphism. Which is well defined up to homomorphism. And for singularity for this dual complex, I just call this dual complex for singularity. I just, by definition, it's the dual complex of the resolution. By definition, is just the DE. So this is just my notation. I just call this dual complex the. Then and I of course hope that the new invariant I defined here is indeed in the same homotopy class. So basically, this M stands for minimal. So that's a dual complex of minimal resolution, though it's not a resolution. It's only a partial one. Yeah, regular complex just means the map from the cell complex. Sorry, for simplex to the boundary is injective. So for instance, this is a regular complex. But this is not a regular complex. This is a regular complex. And the theorem 2 is the so now if we look at a special category of singularity, which I'm going to define immediately, that if X is KOT, then we want to study the dual complex of that. Then out of this theorem, actually, we got this dual complex is always contractible. So actually, before us, it's proved that for quotient singularity, you either use the Berkowitz space approach or use the equivalent market correspondence. You can prove that this dual complex is contractible. But KOT is a much larger category than quotient singularities. And we actually can generalize the statement to this category of singularity. And theorem 3 uses slightly more, but also, but from the idea of 2, we prove that if I have again, x is KOT. So instead of looking at the dual compass, we really look at the link. And we look at the fundamental group of that link. So that's just the local fundamental group of x in X. And but we want to prove the topological fundamental group of this one is finite. We cannot do that, but we just prove the état completion, the profinite completion of this fundamental. So the algebraic fundamental group of this singularity is indeed always finite. I mean, we still conjecture. I think that was in Yang's paper. He still conjecture that if you take out this profinite completion, it's still finite. But we don't have a way to prove it yet.
Sorry, I can't read this.
This is local. Yeah, sorry. Maybe if it's right. X is KOT. Actually, I don't need isolated. Just count multi-log terminal. I'll define this in a minute. So the theorem 4 is you use actually the same approach as the theorem 1, but attack a slightly different situation. I mean, this is actually a conjecture by Weiss. It says that if I have a f, a polynomial, in, let's say, an, so it's an n-variable polynomial, and then I look at the motivic data function. The motivic data function, and then we look at the nth pole. The maximum possible order pole of we look at the nth pole of this motivic data function. Then it's the all possible are just the largest one, so which is just the log canonical threshold of this function. So of course it may have more poles, but if you look at the poles which has the maximum possible order, then the only one can be the log canonical threshold. And I mean, actually the proof is using the same idea as the first one. I mean, so the main goal of today is to prove the same one. And if I have a time, I will talk about the proof of others. Well, okay, I'll talk about this. I mean, in the KOT case, basically well, I'll talk about it. But so let me define what's the KOT. So that's short writing for Kawamata log terminal. So let's say X is KOT. If first X is normal, and case is Q Cartier is always. Now I take a log resolution. And then I compare the pullback of F alpha star Kx. And then I compare it with Ky. And then they only differ by some exceptional dividers. So I write the sum of the exceptional dividers here. And my requirement is that all the AI is larger than -1. All the AI is larger than. So it's very easy to check. If this works for one local resolution, then it works for all other local resolution too. And today, actually, I also want to define another category of singularities, which is the divisorial log terminal. I mean, let's first look at a little bit technical, but I will explain why we need this. So if I x delta, this is just a reduced divisor. Then this is DLT. If, I mean, now x is still normal, but instead of kx is q cut dr, I need a kx plus delta is q cut dr. So you can, instead of pull back kx, you can pull back kx plus delta. And there exists a log resolution, ye to x delta. So this one doesn't hold for all the log resolution. It only works for certain log resolution, such that if I compare with kx plus delta and ky plus, and the Bayesian transform of this, so let me give the name of this y. So first I put a Bayesian transform of it. Then we know the difference will be still some exceptional divisor. And then I still have a ai larger than -1. So if I draw a picture of DLT, it's like this. So first I have some divisor with reduced divisor. And then I have some singularity. So if I want to take this log resolution, by definition, actually, I know that the intersection of these divisors, generically, they are actually it's just a smooth. So then when you take the log resolution, you don't change the generic point of the intersections. You just change outside. And then you compare this about two sides, and then you just get -1. So we need this because this is precisely the category of singularity, which will run MMP for simple normal crossing variety. And then we always end up with a DLT pair. And I think that's how people start to define. Yeah, coefficient 1. Sorry, yeah, coefficient 1. And KLT, I mean, it's also naturally come from lots of other categories. For instance, that means like all the holomorphic function locally on the smooth locus is indeed a L2 integral. So it's actually quite a natural category of singularities. Oh, log resolution just means, so if I look at the ye to x delta, then this part is just the Bayesian transform of delta plus exceptional divisor, and this y. Putting this together is simple normal crossing. Oh, that's just L2. I mean, that's. I mean, for KLT, that just means locally for a singularity. If you have a holomorphic function defined on a smooth locus, then it's L2 integrable. Okay, so we want to construct a dual complex for this more general category of singularities instead of just simple normal crossing variety. Then we have to first cite without they just say that if x delta is DLT, I write delta as the sum of EI. And then the intersection of EI, let's say U1. So you take the intersection of k of them, then it's always normal. I mean, it might not be connected, but it's always normal. And of the right codimension. So in other words, the strata you got by intersect the components of this delta is always normal. Then actually we can define the dual complex exactly the same way. I mean, originally if it's not normal, then you have to choose that so here I use the components. It's not clear I use irreducible components or kinetic components. And for different choice of those, I mean, sometimes plays different role. But if to make my life easier, I just require normal. And then there is a canonical choice. And also, of course, the dimension of the face is just a codimension of E in codimension -1 in X. So that's also canonical choice. So out of this, you know that X delta, if X delta is D of T, I can well define D delta. Without any ambiguity. Oh, if it's empty, we just it's just nothing. It's just nothing. Okay, so why we want to look at the DOT one? As I said, we want to use a minimum program, and the thing is that actually minimum program produce some partial resolution of singularities, which is still not unique. But in some sense, it's more canonic than the adding arbitrary simple number crossing local resolution. Of course, the trait you have to give is it's not simple number crossing anymore. But we have some approach to understand it for some questions. So let me define this. So if X is a singularity, I define the DOT modification is a pair if that first I need this guy is DLT. So I need this DLT. So for instance, any simple number crossing satisfies this condition. But the second condition is more restrictive in that I require that this pair is nav over X. So if you're familiar with minimum program, you know this. You just say that this pair is actually relative minimum model over this X. And actually the usual way to get this minimum DOT modification is that if I start with a simple normal crossing pair, local resolution of X, then I just start to run minimum mode program over X, and then if this program terminates with a minimum model, then it just gives me a DOT modification. So this one is just the one you start with simple number crossing, and then you run minimum program, you end up with this. Of course, I mean, for the expert, we know that there is a difficulty that we are running minimum program for coefficient 1. But no, I mean, if you don't put this E here, it's minimum resolution. But if you put the E here, it's not the minimum resolution. I mean, but it still appears in actually many work on surfaces. I mean, you may pick up some coefficient singularities along the components. So a population is that in our setting up, that if I assume Kx is, if Kx is, I mean, I always assume X is normal, so I won't write it anymore. But if I assume X is Q Katia, then the DOT modification exists. So, because in that case, actually, you can, I mean, the difficulty of this is you have coefficient 1, but under this condition, you can do some manipulation to reduce to the coefficient less than 1 case, and then use BCHM. So basically, the proof is BCHM plus some modification. So we know actually in the singularities we are interested in today, the DOT modification always exists. So, but what's the nice thing about DOT modification? That's in the second population, is that if I have x1, I have a two derivative modification. If I have a two derivative modification and of the same singularity, and then if I look at the dual complex of these two, it's indeed actually homomorphism to each other. So it's much stronger than, it's indeed pure homomorphism to each other. So it's much stronger than homotopic. And the reason to say this is actually also you just look at this picture. So you somehow use weak factorization. But the point is here is that when you pull back, you only look at the dividers which have a coefficient of 1. If you so you have a negative 1 here. But if you want to have a coefficient of negative 1 here, it only comes from you blow up some strata. So if I don't blow up strata, then by my definition of derivative multiplication, I always got some coefficient less than 1. Larger than negative 1 on this side. So in other words, under this weak factorization picture, I only compute the dividers coming out from blow up of a strata. But in this, we already say that if I blow up a strata, it's always a subdivision. So of course, this picture might mess up your homomorphism statement. But in our definition, we already done count it. We don't count it, so it doesn't give any other trouble. So that's how you say the canonicity of the derivative modification, because somehow the dividers which come more randomly, we just don't count it. So out of this statement, we already say that, out of these two propositions, we already say there is a canonic homomorphism well-defined regular complex associated to the singularity. But actually, the main part is to prove that it's actually homotopic to the one. You come up with a simple number crossing one. That's right. No, I mean, as long as it's not 1, I just throw it. Yeah, I just ignore it. Because all of them will be less than 1. Could be negative, even negative, but then I just ignore it. Okay, so we want to prove that it represents dual complex. So in other words, we have to understand what, for this MMP process, what happened. Indeed, out of the proof, you can show instead of simple number crossing resolution, actually you choose any pair which is DLT over this point, even without this NEF assumption. Then the dual complex you construct is always homotopic to this one. So actually, it's enlarged the category of the dual complex, which you can use to define the DRX, the homotopic type. But then among all these different complexes which are homotopic to each other, there is a more canonical one, which is actually well-defined homomorphism. That's the idea of the proof. So, okay, so let me start explaining the proof a little bit more. So now the picture is that I have this singularity, and then I have the resolution. And actually, I can, without too much work, I can assume my resolution is actually over some DLT modification. And this is the DLT modification. So this is the DLT modification. This is the log resolution. And this is given by run MMP. So we basically want to show that the dual complex defined here and here are homotopically equivalent to each other. And the idea is that, I mean, there was an intuitive idea hanging around, but we didn't exactly work it out. But then we just analyzed MMP a little better and to prove this. So the intuitive idea was that now if I look, first I look at two functions we defined. I compare the, let me give the name of this now, G. So I look at the G upper star, K x dot. And then I compare with ky plus e. And then I have to put the correction here, which is, so for the, but, so that's a correction. And then I look at the G upper star, third dot. And of course that will have us give you some other function, bi and ei. And we know, because of the dot assumption, we know that the G upper star x dot is plus delta dot is less than ky plus e. With the equality holds if and only if the ei is a component of delta dot. So for other dividers, if I don't blow up the strata, I mean, I can assume this resolution doesn't blow up the strata, then for others, it's also always a strict inequality. And then this just tells you that the ai over bi is larger than 1. And the equality, if only if that the ei is a component of delta. So I actually call this, I define this as a weight function of the ei. So now I have a weight function which is defined on these dividers, which only takes the value 1 on the dividers appear on the DLT modifications, and then take the value larger than 1 for others. So if I draw a picture, it's like so for instance, I have some complex. Then there is a function. So now I look at the entire complex. And what I want to show is that the entire complex has the same homotopy type along the minimal level. So the DLT modification, the divisor appearing there, are just the dividers appear on the minimal level. So this is so that's very much like a Morse function from some viewpoint. But we, as far as I know, actually we still have no way to show it's a Morse function. But we prove something similar. We prove that, I mean, Morse function without a critical value, except the minimal one. So we prove that. I mean, as I said, this joint work is Tomato and Janosch, is that if I fix any value t larger than 1, then this MMP actually collapse. So if you don't like collapse, you just take it as a strong deformation. MMP actually collapses the dual complex, which you look at all the dividers has weight function less than t to the minimal one, which is just the. So in other words, I mean, under this MMP, you just collapse this, and then if I take a slice, I just look at the thing down, and it's always collapsed to the homotopically collapsed to the bottom one. So particularly if you choose this function large enough, then it will contain the entire all this ei, and of course then it collapses the bottom. It just give the second part of the theorem. Yeah, it's simple homotopy. That's right. That's right. That's right. So how do we show this statement? Okay, let me see. I don't want to read. So, okay. So now let's say if I want to show this stronger statement, then I just compare. So the MMP is given by MMP of sequence of kx plus e, but now I write e as delta, let's say strictly larger than t, and delta less or equal to t. And then since I can choose very small epsilon, then I still basically the same sequence is so this is the sequence for y 1 epsilon delta plus, because I choose epsilon sufficiently small but positive. So originally it's just MMP for this, but since every step is negative, I can add a little bit of perturbation. So it's still MMP for that. Then if I compare with f upper star kx plus t, sorry, DLT, t delta DLT. And I use this, let me give this name, maybe I call ET. Ky plus Et minus this. Then actually I can write it as E minus F. And such that the support of F is the same as the support of the delta, the weight downstairs. And then the support E is, of course, the other parts. So, and both of them are effective. Maybe here I take a small delta out. So I'm adding a small delta, but it doesn't matter. Otherwise, you just take you just put the coefficient 0 part on the right-hand side. So I have this picture. And since now I want to prove that this collapses to this one. So I just look into the support of F. So if my MMP doesn't change F, then change any strata of F. I mean, just doesn't change anything. I just keep going. And if it changes, that means it collapses some strata of this F. Particularly, this generic point of the strata, since it's not contained along EI, that just it changes some locus, which is not contained in EI. So particularly, we got the extreme ray Ri dot. This extreme ray dot EI is always non-negative. Because, as I said, if you change the strata of F, that just means the exception locus, the flipped locus actually is R is not entirely contained in E. So particularly you got this one. But we know that the R dot E minus F is negative because that's my MMP. So particularly that implies the E dot F0 is positive for some F0. And this is actually, you will say this is a crucial thing. Because in general, of course, in run MMP, you may change the topology. For if MMP may just collapse one divisor to a point. Now here you say a point, here you don't say anything. So that changes your topology. But what I'm saying that if I have this kind of F0, this divisor here, then it actually just, it doesn't change anything. Let me draw a picture of what's going on here. And what is the role the F0 play here. So the typical picture in your mind is like you have a 3-dimensional picture and you have a surface. You have two surfaces meets a curve. Then I flip this curve. If I flip this curve, then what I get is just this one. And of course, the dual compass here is the edge with 2 points. But here, since you broke this, it just become 2 points. Of course, under this process, you change the topology. But if I have my F0 here, what's going on is I have my F0 here. Then it intersects this flipping curve positively. So after you flip, it still contains the entire flip locus. So it's a picture like this. Then the picture becomes you have a 2-dimensional cell. And then the picture here is you just have this one. You just have this one. So now you see these two pictures, they are homomorphically, they are homotopically equivalent to each other. And actually from here to here is a collapse, is a simple collapse. The reason that, because you flip this curve, you actually flip this part. You take out this part. But at the same time, you also flip the intersection of this curve with this divisor. So in other words, you change this one, but you also change this one. That's precisely the definition of simple collapse. So in other words, I mean, this is actually, in some sense, the general picture. So I put my F here is the point. Now let's say my MMP wipe out this V. So let's say MMP wipe out this V. But the existence of F0 has this property. That means F0 connects with every point. Meets every fiber curve. And using a connectivity, we actually show that connectivity theorem. We actually show that when you wipe out this curve, you always the way always actually lives in the link of this point. So so by saying it's a link, you actually have this W here. So so if you have if V, then W, this is some connectedness lemma. So then you wipe out the V, you have to wipe out W. So the V always lives in the link of this. And but the second worry you may have is that now let's say I wipe out something. But how about I just wipe out this part? So I might just wipe out this W, but not V. But again, this cannot happen. This is if W, then V. This comes from it's an MMP sequence. So that tells you the V and the W always come together. So that, I mean, when you wipe out the V and wipe out the W at the same time, that's just a simple collapse. And if you group if you put all of the simple collapse together, that's just a collapse. So that just precisely tells the statement that if I run MMP, this basically collapse to that one. So the point here is that we have to find out this F0. Then you just look at the MMP status and use some connectivity theorem to show that that each step there is V and W, they come together.
And what is the KOT coming here?
Oh, I haven't said what KOT should. Yeah, I haven't used KOT yet. I mean, so for the first element, there is no KOT, right? I mean, there is just say there is a dual complex.
Yeah, but in some sense, it's kind of the same type of thing.
Yeah, the point is that if I have a DOT modification, it always comes from running MMP of someone, of some simple number closure. If you don't assume DOT, if you don't assume DOT condition here, then you run MMP, you just get some other pair. This pair guarantee that if you start to run MMP of this one over this, it just come back to yourself. Well, you will see from the proof of the next statement. So now I want to prove the theorem 2.
So here somehow you lose, I mean the main statement isn't it that you lose the divisors with coefficient less than 1? The one that got not in here,
That's right. I mean, on this process, basically you actually lose all the coefficient of 1 automatically. You lose automatically, and you may lose more. But this argument just tells you when you lose them, you don't change the topology. Yeah. So that's right. The DOT just tells you the DOT modification already tells you that the coefficient which is less than 1. Actually, you don't say there. But then this argument tells you on the way you don't say them, you don't change anything.
Yeah. And the second proof of the second statement.
That's right. That's how the second statement works. But I mean, you have to be slightly more careful that the theorem 2, the proof. So X is KOT. Basically, the equivalent to saying that the DOT modification is the same as itself. So you basically don't change anything. Then you actually cannot really come up with a DMR in some sense because it's an empty set. Of course, you have a dual complex. I mean, it won't collapse to an empty set. So, but the slightly trick here is that I find the edge. I mean, so in some very general predation, maybe such that if I look at the x epsilon edge, so that edge is some divider in some general predation passing through that point with some careful choice coefficient, such that the DLT modification of this one is of the form that x DLT. And then here, of course, I work with coefficient not exactly 1, but doesn't change that much. That I first have the Bayesian transform of epsilon h. But then, because of the choice of my epsilon h, actually I only extract precisely one divisor. So this is irreducible. And actually, we call it a Kola component. I mean, it's not unique because I mean, in some cases it might be unique, but in general it depends on the choice of epsilon h. But nevertheless, you can find this. You can, after adding auxiliary divisor, you actually can have this picture, which only extracts one divisor. But then you just run the same argument again. That just tells you the dual complex of x in x, which is precisely just collapsed to the dual complex of S, which is just a point, because S is irreducible. So that's just equivalent to say this guy is this one is contrastable or even is collapsible. So that's how we prove the theorem too. So I still have a few minutes. So now let me talk about the proof of theorem 3 because it's a conference for fundamental group. So for the theorem 3, we actually have to look at the geometry of S a little bit more. So now we look at this Kola component, and we take the restriction of Kx plus S, restrict on S, which I write it at K plus some, let's say delta S. I mean, in general, if this is simple normal crossing, you don't have this part. But since you may have some coordination 2 singularities on this, then you just have to pick up this divisor, effective divisor. But it doesn't really matter. But the point is, this one, by choosing the DLT modification carefully, you can assume that this guy is ample. So you actually, basically, you just extract like a log Fano varieties. Just extract a log Fano variety. So now let's say I want to prove the fundamental group is trivial. I have a sequence of movism which is at outside this point. I want to prove it stabilize, and then it will be just terminate. It will just stabilize. Then this is I have this construction of x DLT as here. So I have this construction here. Then I just take the product, continuing product for on each level. So we just take the production. Then it has some properties of this. Of course, when you branched over one divisor, I mean, you make a quite complicated picture here. But because of the singularity property, the DLT singularity property, actually in this case it's indeed the PLT, will imply that the SI DLT is always irreducible. So here, not just the first one is irreducible. I mean, the latter ones are all irreducible. They don't meet each other. Oh, sorry, I'm sorry. there are no other components, because if there are other components, they must meet each other. Then just break the pair decomposition. So they are irreducible. And if I call this the pullback of Ks plus delta S is indeed the Ksi plus Si. Sorry, I don't put DLT. This is, so in other words, they are all log Fano varieties. So now I just have this sequence which is eta outside one divisor. It might branch over that divisor, but for that divisor, I just cook up a sequence of Fano varieties. Then it's a result by Haken, McKernan, and myself say that the degree is bounded. So the degree is always bounded. So that immediately tells you Sm is equal to Sm plus 1 for m large enough, because you cannot increase your m to infinity many times. So now I just have a picture that I have some Moividen between varieties which branched only over one divisor, and after a while that divisor actually stopped to branch. Then you may still have some like inertial group, but then using some cohomology calculation, you will say after a while that will stop too. So that tells you x m plus k is equal to m plus k plus 1 for k is sufficiently large. So that's how we got this. We got it. So the idea is we basically just cook up this construction of extracted Collar component, and then use the abundance of Fano varieties, and then come back. And then there is the theorem 4, which is slightly looks in a different language context with what I have proved, but in the end actually it's just a very similar idea. So let me just state what the statement which the geometry statement which it boils to. This statement about the poles of motivated function. So now let's say I just take a log revolution of ye to xf again. And now originally I defined the function ai and the bi, and I said that function actually determines a lot of the topology. Here I also have the function, the weight function. The weight function is defined in this way. I define ai similarly just by compare the product of kx and the ky plus e. Oh, I'm sorry. Let me say. Okay, let me call this G. So I still compare so this is still the log discrepancy. And then I still compare the divisor Vf, and I compute the multiplicity along EI, which I still call it BIEI. I still call it BIEI. And then I define the weight function to be still the same, like AI over BI. And we know that the minimum one of this guy will be just the log canonical threshold. So that's the log canonical threshold I said there. And then the statement is just that, let's say if I have a maximum cell, in this complex. So maximum cell in this complex just corresponds to that I have a EI, which is of zero dimension. And then I want it to be the pole, maximum order of pole. So the pole, the possible pole will be just the number of this. So the n-dimensional pole. Okay, let me first print that. If the VE1 is equal to the weight of E1 is equal to weight of En. Here, let's say I is equal to 1n. If all of them are the same, so because we know the pole, if you can have a pole, that must be this situation. You must have some local resolution and satisfy that the intersection at one point and all the weight are the same. And then the conclusion will be, okay, maybe I just write here. The conclusion will be just then this weight is indeed just the low canonical threshold, is the minimum one. So originally you just know the weight, along all the dividers which intersecting this point are the same. And then you just conclude it's the low canonical threshold. And the idea is you look at the complex. And then let's just say you have on some level set, you have a maximum dimensional cell. But then you know that out of this proof, you know basically this complex will collapse to the minimal one. So the topology is always on the minimal. So then you expect that there is no high maximum dimensional cell in any weight which is larger than the minimal one. Because otherwise, usually that will give you a non-trivial topology. But of course, this is not a strict proof. But then again, then you just use this MMP process to analyze it. You just get this statement. Okay, I'll stop here. Thank you very much.